went and hit a couple locations out in the field, and in particular we hit Temecula. And well, I have a little video to show you, and afterwards I will show you some of the math that is involved there. But first, check our little video out and we'll be right back at you. Hey, Mathman Dan here. You know, here at the College Math Line, we like to show you how math gets used in the real world, and well, guess what? We are out in the real world today. Actually, behind me is Lake Skinner, which is a very large reservoir just outside of Temecula in Riverside County. And in fact, in addition to being a recreation area, you can boat and fish here. All this water behind me provides drinking water for 2.5 million people throughout San Diego and Riverside counties. So I looked at the official website for this reservoir, and according to the website, the surface area of this lake is about 1,400 acres, and in fact the amount of water in here is about 15.8 billion gallons. So my question is, hey, how'd they come up with these numbers? I mean, I really doubt they're going to drain the lake and try and measure all that water, right? Well, there are some mathematical techniques for trying to estimate values such as these, and you know, some might seem like common sense, but actually there's some sophisticated ones that I doubt you and I would come up with on our own, but they can be surprisingly accurate. So back in the studio, I'll show you a little bit about how those techniques work, and we'll see maybe how they came up with those numbers for how much water is in that reservoir behind me. You know, I checked their website again, and I said 1,400 acres, and now their website says 1,200 acres. So I'm not sure if I misquoted that or if they changed it. I'm going to go with they changed it. No, they probably didn't. But anyway, so how do they figure out how much water is sitting there? You see this big body of water. It's kind of hard to just, you know, stare at it and say like, oh, I think that's so much acres of surface area there. No, there are much better ways to do it. And I'll show you one that's kind of basic. You could come up with on your own. And then I'll talk about one that's a little more sophisticated that at least I certainly couldn't come up with by myself. But good old Google has these wonderful satellite images. So I loaded up the image of the lake, and I have it here on my computer. And there's even a scale that you can, you know, measure how wide the lake is. So here's one basic thing you could do. You could just overlay a grid onto the lake, and you could count how many squares cover the water that you see in the lake. And because Google supplies a little scale, I can actually measure this. And I designed this grid so that it's 1,000 feet on each edge of that square. And so what would you do if, you know, well, one of the squares didn't have complete coverage with water? You'd have to estimate how much water is in a square, like, you know, it's half full of water or a third of full. But if you total up all the squares, you can come up with how much surface area you have. And each of those squares actually, it's 1,000,000 square feet per square, believe it or not. But I figured it out. It comes out to be about 23 acres, I believe, per square. So you could do that and get a reasonable estimate. Well, what if you want to make the estimate a little better? One thing you could do is make the squares smaller. It's more work for you, right? But ideally, you could get closer to the true answer. So I did that. I made one more grid, and on this one I made the squares twice as small. And again, you could go through and see how many squares are covered with the water and how many aren't, and total up the value. And believe it or not, this is related to a calculus concept where if you made this grid smaller and smaller and smaller, you will get closer and closer and closer to the true value. Depending on how much patience you have, you could get incredibly close to the true value, you know, within practical purposes of how far you actually need to take this. But there's a more sophisticated technique that is called Simpson's rule. I'm going to say it's named after Homer Simpson. I'm not sure what the guy's first name really was, but I'll show you the concept. And this, again, I would not have come up with this myself, but what you would do is instead of making squares across the lake, I would cut it into strips. So you'll see I have on my computer, I took the lake and I cut it into actually 16 pieces, and I made sure that each piece was 1,000 feet wide. And then all I have to do is measure how tall on my screen each of those pieces is, you know, according to the scale that I have. So each of those yellow bars you see, I would measure the overall height of that bar. Now there's a formula we're going to use to figure out how much area is included in this lake, and I'm going to show you the formula. I'm just going to let you see it, and you can decide if you, well, I would never come up with this on my own, but it's on my math cam. So here's the formula. It's called Simpson's rule, as I mentioned, and if you look what it says take the width of each strip. Now I had them 1,000 feet wide each, so my width right here would be 1,000 feet. Divide that by 3, and then multiply by all those heights you're going to measure, all those yellow bars in my picture, and we're going to add them all up. But you're not just going to add them up directly. You're going to have the first one, which I numbered 0 as the left edge. The next one you're going to have 4 of those, 4 times that height. Then you're going to have 2 of the next one, then 4, then 2, then 4, then 2, then 4, then 2, and continue until you get to the very last one. Now, I don't know about you guys, but that looks weird to me. I mean, why would you have this strange combination of 4s and 2s, and what does that possibly do for you? Well, there is some logic to this. In fact, I can give you a brief idea without going crazy of what it's doing. I printed out my picture of my lake, and in fact what you are doing when you use Simpson's rule is you are using these height measurements to make little parabola shapes on the ends of them, and you're using that as an approximation to what the lake is doing. It turns out that's actually a pretty good way to approximate things that aren't straight little line segments, is to use parabolas. That sounds very complicated, but luckily, if you take these in pairs and make these little parabola shapes, when you add them all up, it makes this nice little pattern of the 4s and the 2s that you saw in my formula. So you take those measurements, you put them on there, you add them all up, and you're going to get a value for the surface area. And it turns out that you will have a closer answer with this method with less time of yours spent. In other words, you could get away with a lot fewer subdivisions of these little strips than on those squares where I might have to make a lot smaller squares, make a lot more work for myself. So anyway, if you want to check it out for yourself, you can see if your estimate for the lake matches up to their website. Their website says 1,200 acres, so you can see if you think they're accurate. I'm going to trust them for now. Hi, I am Mathman Dan, and I am here with Scott from Caltech, and we are standing on the outer perimeter of the Palomar Observatory. Well, actually, I was going to say the dome, but this is just the largest dome. You actually have 6 domes, 6 telescopes.
That's right.
So, Scott, with this one, do you really need more? Isn't this one enough?
Of course not. We need as many telescopes as we can get. And it turns out they do different things. So you can have telescopes that are automated to work on a certain project, or telescopes with a wide field of view or a narrow field of view, or ones that gather a lot of light and ones that don't gather as much light.
So this one's so large, but what controls how much light they get?
It turns out when we talk about the 200-inch telescope, that refers to the opening, or the size of the mirror, and that really is the area of the circle of light that hits that, tells you how much light you gather.
So this guy over here, I assume he has a much smaller, I don't know what size that is.
That's an 18-inch telescope.
18-inch. Okay, so the mirror you're talking about, or you've called it an aperture before.
Sure.
All it is the area of a circle, how much light you're going to get.
Right.
So if we could figure out the area of the circle, we would know proportionally how much more light this guy's going to get.
Right.
But you also mentioned to me that that one sees more of the sky than this one, even though this one's much, much larger. So how come?
Well, it turns out also that the shape of the parabola for the mirror determines how that light comes to focus and how much sky you see.
All right, so you said parabola. So some of our algebra students are familiar with parabolas.
I hope so.
So the shape of the mirror here will reflect the light, and this is a larger mirror, but it's reflecting it in a way that's a narrower part of the sky. So you would see the whole sky with this one, or more of the sky?
You'd see a lot more sky with that one. It was set up so that you get, the way that light comes together to focus, you actually see more sky. So that makes it very useful for hunting for objects. So we found many comets and asteroids with the telescope that's in the dome back there. And then here you see a much smaller piece of sky, but a lot deeper, because you get a lot more light.
So once you find something interesting with that guy, then you tell this one where to look.
Right.
And all that's determined by how large the area of the circle is that's collecting the light.
That's right. And the curve.
And the shape of the parabola and how it's focused,
Right.
because you can change that.
Exactly.
All right, so we can show that a little bit in the studio afterwards. You also mentioned to me that the light is measured on a logarithmic scale, and I know my students love logarithms. So maybe you could tell us, why are logarithms used to measure the light that comes in?
It turns out that the scale that was devised, actually long time ago, was set up so that the brighter objects have smaller numbers, even going into the negative region of the scale. And that for every change of 1 magnitude, you've changed in brightness about 2.5 times.
So if I had one that was a -10 and one that was a -5, those are not twice as bright as each other.
No, it's 5 steps, 2.5 times 2.5 times 2.5, 5 times.
Which gets much, much larger.
Right.
So that's
much larger.
If you multiply 2.5 over and over and over, we're basically talking about an exponential function.
That's right.
Which would explain, since logarithms are the reverse, why we're getting a logarithmic scale.
Yeah.
So how bright is the sun?
So the sun is very bright, and it's -26. And you want to compare that maybe to if we were outside at night on a moonless night away from the city lights, the faintest that you and I could probably see is about 6th magnitude.
+6.
+6. And the
Okay.
faintest that this telescope can see is about 27th magnitude.
So if we went from the sun to what this can see, we'd be going 2.5 times, many times over and over. It's a very, very large differential there.
Yes, huge.
Okay. Well, it makes sense to me why logarithms are in play here. We'll follow up in the studio, and I'll try and convince you guys why logarithms are a good system to use for the measurement of this light. Scott, I want to thank you very much for showing us off your telescopes. They're very impressive here. We're very thankful for your time.
You're welcome,
Hope
Dan.
to see you again sometime.
Yeah.
So our good friend Scott, he mentioned actually several different areas of math that come into these telescopes, and one thing he mentioned was the mirror. And by the way, you probably couldn't tell, but it's not like a little telescope you hold up to your eye. It's humongous, but there's a huge mirror in the bottom that actually the light hits first, and then it bounces to a camera. So one thing he mentioned was, how much light these things collect, and they have 6 different telescopes up there. The largest one was 200 inches, and the smallest one was 18 inches. And in fact, I brought a picture of the largest one with me. Just the mirror is on the telescope, which normally is hidden, but here's it disassembled. So I believe it's actually coated with aluminum. They shine it up super shiny so it can shine the light in there. So you might think, okay, well, I've got an 18-inch mirror and a 200-inch mirror. So let's see, 200, if you divide it out, it's about 11 times more than 18. So you might think, okay, that's going to let in like 11 times as much light. Oh no, not even close, because as Scott mentioned, it's based on the area of the mirror, and it is a perfect circle, of course, and I bet you guys remember the formula for the area of a circle. So I will show you on my math cam how much more light the big mirror is actually going to collect, because I have the area of a circle written on here, and I'm just going to make a simple ratio. So the fraction on top, I'm having the area of the large mirror. On the bottom, I'm having the area of the small mirror. Want to make a guess how much larger in area the big mirror is? Well, I did it on a calculator. It comes out to be about 123. So that big mirror is collecting 123 times more light than the small one. But interestingly, Scott mentioned that the small mirror actually sees more of the sky, and that had to do with the shape of the mirror. He mentioned that was a parabola. So if you had a little bit of algebra, you've probably seen parabolas in your class, and I brought a parabola with me. Here it is on my Etch-a-Sketch. What do you think? Oh, I'm just kidding. I have a better one than that. All right, so that was just for fun. I do have a good one on my computer. This is a parabola, and one of the defining properties of a parabola is that it reflects the light rays right to a central spot, this red circle I have here called a focus. So if you put the camera at the focus, it will collect all these light rays just perfect. And if you change the shape of the parabola, which is simple to do by modifying the equation just a little bit, you can spread those light rays out, or you can concentrate them very narrow. So this way you can control how much of the sky you actually see, regardless of how big the mirror actually is. It all depends on the shape, and you would place the camera where the red focus dot is, and you would make sure you collect all the light in focus. Another thing Scott mentioned was that he mentioned a logarithmic scale for measuring how bright stars are. So I thought that was kind of interesting, and why a logarithmic scale, and why did it go the way it did? In fact, he was using negative numbers to measure the brightness of the sun, for instance. So I did a little digging, and I found out how this system actually works. And it turns out historically that they decided, this is a long time ago, they were just going to number the brightness of stars from 1 to 6. And they tried to make it so that each number up was roughly a difference in brightness of double. So I'll give you a little example here on my math cam. This is what they tried to do. They tried to have, the faintest one was measuring as a 6, and the brightest one as a 1, and then they had to, these 6 stages of magnitude, they called them, and they tried to make it roughly double. Well, that was a kind of crude measurement, so in the 1850s, they decided to make it more official, and what they decided to do is say, hey, we're just going to say that from 6 to 1, these are like the dimmest and the brightest stars you can actually see with your naked eye in the sky. We're just going to say it's going to be 100 times different. So we'll just say that the brightest one here is 100 times larger than the 6. And they decided to measure them in a decreasing order. So if you think about this, it means that every time you go up one stage, like from a 5 to a 4 to a 3, it's not a nice multiple like double, in fact. You'd have to figure out how you would do that. If you place the intermediate numbers in there, you can actually measure, okay, each time I go down a number, I'm going to multiply by the same amount of light each time. So let's just call this something like B. I'll say I'll multiply by B each time. Well, if you count down, I'm going to have to do this 5 times in order to get 100 times brighter. So if you think about that behavior, what you could say, I bet you guys know a shortcut for writing B to multiply by itself over and over. You could say B to the 5th power is equal to 100. So that would have to be true if B is the multiple on each step of this measurement system. And if you just solve this, B becomes the 5th root of 100, which is about 2.5. So Scott at Palomar Observatory actually mentioned that each order of magnitude is about a 2.5 times difference. And this is where it's coming from, so that 1 from 6 came as a perfect 100 multiple. So this also explains why he was using negative numbers, because if you keep going brighter and brighter, these numbers will count down to 0, then -1, then -2, etc. In fact, the brightest star in the sky is called Sirius, and that one is about a -1.47, I believe. So if you want to see how this works and to get a hint as to why logarithms come into this at all, what we could do is just compare two objects I bet you are familiar with, a full moon and the sun. So a full moon measures about a -12.6 on this scale. And the sun, which is obviously probably the brightest thing you're going to see in the sky, is -26.7. So Scott mentioned it was about a -26. So if you look at the difference in these values, this is about this, I think, 14.1 difference. So, if you weren't thinking about it, you might say, well, okay, that means one's 14 times brighter than the other. Not true at all. This is actually the power of 2.5. So every time you go up a number, you're taking a multiple of 2.5. Really, that's linked to an exponential function. So what we could say is you take 2.5 and you put the 14.1 as an exponent on there. This is how much brighter the sun is than a full moon. And if you do this out on a calculator, I bet it's a lot larger than you were thinking. This is about 408,000. So literally, you could say the sun is 400,000 times brighter than a full moon. It's called a logarithmic scale because the numbers you use to measure the brightness are actually exponents. So the 12.6 is really corresponding to an exponent rather than the actual value. The same system is used to measure earthquakes and sound, as well as other kinds of measurements where the numbers get extremely large. It turns out looking at the exponents is actually a more convenient way to measure the differences. So, we'll talk about the earthquake some other time. That's interesting on its own. But I would like to say, if you ever get a chance to go up to Palomar Observatory, if you're in the area, it really is interesting, and there's some beautiful scenery up there. And you might talk to our good friend Scott, who knows. Today's little mathematical snippet is inspired by this weekend because it is Earth Day on Sunday. And so there's lots of talk lately, especially in the political arena, about global warming. And so I thought I'd show you a little bit of some data. There's some debate on what's causing global warming or to what extent humans are responsible, and I'll leave that to the political debates. But I'll show you some hard facts and what math maybe has to do with it. So what I have, in fact, I have this on my computer. There's a graph we found of carbon dioxide levels, and these have been measured every month since 1957, I believe. And they're currently measured at Mauna Loa Observatory. I believe that is in Hawaii. So if you look, I know the graph's kind of thin there, but if you can see it, it fluctuates a lot throughout the year. But overall, the trend has been up. So what I did was I took the numbers from every March, since that's the most recent data they have published is March '07. So I went back to 1958, which is the first March they had, and I put all these numbers into my little calculator. Now I happen to have with me a Texas Instruments TI-84. It's the same calculator a lot of my own students have. So if you have a similar calculator, my screen's going to look just like yours. So what I've done is I have all these data entered, and there's a whole bunch here. What I did is I made a little graph of them. And so you're not going to see mine fluctuating because mine is just March every year, but you do see kind of a steady increase. And what analysts can do, researchers, is they can try and express the trend mathematically. So I have a whole bunch of various formulas that we're going to try and see if you think fit the trend. And it's kind of hard to come up with some of these formulas by hand. Luckily, my calculator has a built-in feature to do it. And what we're doing is called mathematical modeling. So first up is, I don't know if you can see that equation, but it's a good old mx plus b. That's a straight line graph, a nice linear function. And if I graph that, it does express the upward trend, but it's really not the best fit. So I think we could do better than that. And a scientist might want to decide what the best mathematical form is, and maybe that would let us more accurately predict the future if you can find out what the past 40, 50 years has been doing. So linear, I think we're going to throw that one out. Let's try another one. The second one on my list is an exponential. And that is, I don't know, it's kind of a crazy numbers you see there, but it's a power of x on the base there. And if I graph this one, you'll see it does get the curve more than the late straight line one, but at the end there, I don't think it fit the trend the best. And an exponential is a good one to try because you get exponential functions if the percentage remains the same year after year. So if every year was increasing 1.5% or something, you would see an exponential graph. But it isn't fitting the best. So I'm thinking maybe exponential wasn't really it. Let's try another one. This third one I'm going to try is a parabola. So if you were in an algebra class, you've probably played with these guys, or you will at some point. So this is a quadratic function. And if I graph this one, that one really seems to fit the trend quite accurately. So if I had to choose, I would probably pick the quadratic one to say, this is what the trend has been doing since 1958, and if nothing else changes, I could possibly use this to predict what's going to happen over the next 10, 20 years. Now, the farther I go out, the less accurate it's going to be. So this idea of mathematical modeling, you're trying to predict the future from something you're observing in the past. Well, there's obviously lots of risks with that, because maybe we will change our behavior, or maybe when we determine everything that's causing it, those things will change and it'll affect. But if I can determine the most accurate mathematical formula now, it's a good way to try and estimate what will happen, at least in the near future. I have one more option to show you. There's a fancy function called a logistic function, and this one often fits populations where they start to level out. And if this were actually the true fit, it would be great, because of much different behavior in the long term. So let me show you that one. And this is the more sophisticated of the four. So I'm going to turn off the nice little parabola we had. This one, I don't know if you can see that equation. It's kind of complicated. It's a fraction with e in it and all kinds of crazy stuff. But if I graph that one, oh wait, it would help if I turned it on. Let's try that one more time. That one, it fits the trend pretty well, actually. The advantage of that is it starts changing its trend afterward. And I'm going to zoom out just so you can see this. It fits the trend pretty well, but then it changes its tune and it starts leveling off. And in fact, if I zoom out again, you'll see it actually levels pretty flat after a while. So if that were really the reality, it would be good news that at least it weren't worsening the carbon dioxide levels. What would be even better news, of course, is if those turned around and came back down. So just a little light idea of what could happen. Now, if you go to any websites that discuss the carbon monoxide, or carbon dioxide rather, you'll see much more sophisticated techniques where they're trying to estimate what could happen in the future. This is kind of a basic idea, but it is a basic idea of what they call mathematical modeling, which is trying to fit a mathematical formula to something you observe in the real world and to use that to make predictions, either in the past or the future. So I think ours are, that one, that fit pretty well. It wouldn't be too bad. So if you are going to be around this weekend, especially if you're a local, we have some activities going on. In fact, I brought, just for fun, I brought some nice pictures of the Earth, inspired by Earth Day, of course. This is for Earth Day, and these are stolen from NASA. I shouldn't say stolen. These are shown as a courtesy of NASA. So these are some shots they've taken from spacecraft, and there's some pretty cool shots of the Earth here. It's supposed to inspire you to take good care of your home, right? This is the moon viewed from the Earth. This is the opposite. If you're standing on the moon, what the Earth looks like. Famous photo taken from one of the missions. This is a really cool photo you can find on NASA's website, which actually shows the Earth at night, and they've time-lapsed it so they have the whole Earth stitched together. Now, in addition to that, if you want to check out some of the data we've shown on the carbon dioxide levels, there's a couple websites you can check out. This is the National Oceanic and Atmospheric Association, part of the government. This is NOAA.gov. They have lots of stuff there. We also have, this is a site at NASA, it's earthobservatory.nasa.gov. They have lots of stuff there. This is partly where I found all those cool photos. And if you are a local, we have some things going on. There's a nice Earth Fair going on at Balboa Park this weekend down in San Diego. That's on Sunday. The Earth Fair, they have lots of vendors and stuff to show. We also have, right here at Palomar, we are having a beautification of our arboretum. We have a really cool arboretum here. On Saturday, they're getting together to try and tidy things up, and they have a cool barbecue lunch going on. So if you want to volunteer your time and help out with that, there's lots of good people there. And we also have a Palomar group organizing a beach cleanup at the Oceanside Pier on Sunday. So lots of things to do if you're local around here, and I'm sure if you live elsewhere, there's stuff going on for you this weekend as well. Because I don't know if you heard, but they're actually raising the postage rates. So people send fewer letters than they used to with the internet, but sometimes you still have to send some stuff through the mail. It's going to cost you a little more come May 14th, I think is the date. So a little trivia first, just for fun. We're going to talk a little bit about what's going on with the postal rates, but they're also later this month releasing some Star Wars stamps. And we are fans of Star Wars here. In fact, our good friend Darth Tater is back with us just in honor of the occasion. Darth Tater, have you seen him before? He's pretty cool. All right, so I actually have pictures of these stamps. They're not out yet. You can't get them yet. But if you do like the Star Wars movies, it's kind of cool. So I'll show you what the stamps are going to look like when they come out. I think these are available. I think it's the 25th. So let's go quickly through. There's a few of these here. I didn't count them, but here's all the various stamps you can buy. Soon, anyway. Just for fun. So why do they make stamps like this? Just so the post office will look cool? Well, no, I think it's so you'll buy them and not use them. Then they make money, right? So anyway, in addition to this, I thought this was very cool. They actually dressed up some mailboxes to look like R2-D2. And I did not see one of these myself in person. This is a picture off the web. But apparently these were really out and around. So if you saw one, I don't know, maybe kind of lucky thing. So Star Wars stamps, if you want to check them out. Now, a couple other strange things are going on. This is a first, I believe. They're releasing this thing called a forever stamp. In fact, I think you can already buy this. And you notice there's no amount on there. The Star Wars stamps actually said 41 cents. This one doesn't have an amount, it just says forever. And their idea is, okay, what you can do is buy the stamp now and it'll always be good for the current postage rate no matter when you use it. So it's kind of like, you don't have to worry about if they raise the rates if you already have these. So that got me thinking, is that a good thing to do? Should we buy these now and stock up on them, or is it really not going to make any difference? So we'll investigate that in just a moment. A couple little bits of trivia for you just for fun. The very first Postmaster General, guess who it was? Benjamin Franklin. I didn't know that. Well, you know it now. And also, a couple other funny things. When the post office was first going before the early 1800s, they used to charge on how many pieces of paper were in the envelope. Well, they gave up on that. And they later used to charge for how far the letter was going to go, how many miles. So, a certain number of miles, they would charge you more. Well, they gave up on that, too. So now, of course, one stamp gets it anywhere you want, even from here to New York or wherever, which is kind of nice. So we'll look at the values in a second. One more thing, though. If you happen to be rummaging around in, I don't know, maybe your grandmother's attic or something, and you happen to come across one of these stamps that I'm showing on my computer, that stamp is one of the rarest U.S. stamps. And in fact, a block of 4 of those sold a couple years ago for over $2 million, I believe it was. So, look around. If you happen to find a stamp that has an upside-down airplane on it, by the way, the airplane was not supposed to be upside down. It's rare because it got a printing error, and usually the post office catches them and destroys them, but they missed that one. It got out. I think there's only 100 of those, by the way. But you never know. Maybe Grandma has one stored up there, and you're going to become rich over a stamp. All right, so what we're going to look at is what the postage rates have done over time. And this is interesting. So I have here, I made a little graph for you. These are the postage rates. And I know those points are kind of small, but hopefully you can kind of see the trend there. And in fact, in the early 1800s, it was only 2 cents to mail a letter. And it went up to 3 cents briefly, and then they actually dropped it down to 2 cents. I don't know, maybe there was a revolt. And it's been going up ever since then. So what I thought was, hey, does this seem right? Or is this just, inflation? Or is maybe this a little unfair? Are they raising the prices too fast? So I also compared this to the inflation rate. The government publishes all the rates for inflation. So I thought what we could do is make a mathematical graph. And I'm going to put both the prices of the postage on there and the inflation rate. And they have a way they measure inflation. They use a number. And what I did was I scaled it so that it would kind of match the postal rates, just to see if they're in sync or not. So here's the answer. And as you can see, the red dots are the inflation and the blue dots are the postage. They're pretty close. So far, it does seem like that it's pretty fair, that they just seem to be matching inflation. And in fact, you can also go to a government website and they have an inflation calculator for you where you can say, okay, if I had $10 in 1980, how much would it be in today's dollars? And they have ways of measuring how much buying power you get. What really is $10 worth? What does it buy you? So I did that as well to the stamp prices, and you might be surprised, at least I was, what it turned out to be, because if you look at the rates, from 1917 it was 3 cents. Here, I'll make this a little bigger, maybe you can see a little better. It was 1917 was 3 cents. And then in today's dollars, that's 48 cents. So they're actually paying the equivalent of 48 cents to a lender back then. And you can look, it jumps around a little bit, but in 1975, it was actually 50 cents equivalent. And it's been 41, 42. So really, the current price at the bottom there, 41 cents, it doesn't seem that out of line. So I have to give my apologies for the post office for originally feeling a little bit like, what, you're raising the rates? Seems like you just did. Well, it still seems like that, but. Okay, so one more thing. I put these rates on my calculator. So I have a nice graphing calculator with me. This is a Texas Instruments graphing calculator. TI-84, which many of my students have, exact same thing. So what you're going to see on my calculator on your screen is just what you'd see at home. This is a graph of the prices of the stamps. And this is from the 60s to the current. I didn't do the really, really early ones. But if you look, there's a definite trend. And in fact, I thought the trend was pretty much linear. So if you've been in an algebra class, you might have been talking about mx plus b. What I did is I made up an mx plus b equation to fit this. And if you notice, it actually does fit pretty darn well. So 2 things we can point out about this. If this trend continues, and the trend looks pretty good, it should be able to let us predict the future, what's going to happen with stamps. And also, if you've been in an algebra class, We're going to do a little quiz here for you. What I want you to do is look at the equation I have. I know the numbers are crazy, but you see 0.0091 something something and then an x. That is your slope. So think about what is that slope actually saying if this equation is accurate. And it was pretty close. Well, that's 0.009, and the slope is always measuring a rate. So what this says is on the average, since the 60s anyway, stamps have been going up about $0.009 per year. That's 9/10 of a cent per year. So that's on average what they do. Well, I also made a list on my calculator of what the prices could be going into the future. So I'll show you those. These are, well, let's see, I have several values set up, and the first one, by the way, this 30, I started measuring at 1970, so 30 would correspond to the year 2000. And if you look, this would be 2007 right now, and it does say we should be about 41 cents, $0.41 roughly. So if you want to go predict the future, I could tell you that it's going to hit 50 cents around 46 or 47 years after 1970. So that would be 2016, 2017, you can expect a 50-cent stamp. Unless things go crazy, right? But I mean, that trend's been there for at least 40 years, maybe 50 years. All right, so now you feel much more educated about the stamp prices, right? And you won't feel bad when they actually go up to 41 cents. Well, there's a silver lining. When they go up to 41 cents, you can use those Star Wars stamps.